Hello, welcome back to the stream. I'm Jun-chan, and we're back doing some Purescript and some Comonads shenanigans. I just felt like going back to it for a bit, and I'll explain why. Well, one of the reasons is that I want to take a little break from this Purescript React Basic Explorer, and the other reason, and let me do some basic housekeeping here. September 21st. That I did something off screen the other day, which was actually let me create a new file for that. Graph Comonad. What did I do off stream? Let's start a new window. I submitted a pull request to Purescript FGL, which is a Purescript port of the FGL in Haskell. I'm going to need to log in. I am logged in. Okay, good. And right, that means that I have the fact that I'm zoomed in to 250 means that I have the tablet layout here, but that's fine. Right, so what did I do? I submitted a pull request, which basically was something I picked up elsewhere, right? The Comonad of graph decompositions, which is Runar's blog post. Runar is one of the really smart people in the functional programming community, and suppose this is his blog. I didn't spend too much time here. About there we go. Software engineer in Boston. Oh, Aloti, thanks a lot for the follow. How are you doing today? So yeah, Runar is a very well-rounded developer, obviously, but mostly doing Scala these days, and wrote a book on Scala. And yeah, I think pretty close to folks like Paul Chusano, who's doing Unison. So and also had this reading group on category theory, and talked about various things on in conferences and whatnot. And so this is obviously coming, let's say, with quite a bit of reputation. And yeah, this blog post basically says that there's two different graph comonads. There's one that that basically peels away the comonad in some ways. Is the graph of context that can be reached. How is it said? The substructure of the graph. Okay, and the other is rotation, where if you're on a sorry, and I should explain what this is. I'm just jumping into the Comonad right straight without any introduction there. Well, to be honest, this is not going to be easy to pick up if you never heard of Comonads before, but maybe this will give you an intuition, actually, because Comonads have two main concepts to them. One is that you can always extract current value, and so here, if we say our graph is a comonad, then the current value is the value under focus. So basically, we're talking about graph with focus, and here you see that actually what I submitted is called pointed graph comonad. That's following some work that I saw in Haskell that was also basically implementing a comonad instance for the original FGL library in Haskell. And so extract for a pointed graph or focused graph is going to be whatever node is focused. And then the second operation that a comonad has is duplicate. And duplicate makes it so that it will basically put the whole structure into each of the slots of the existing structure. And the question is, okay, you can put a whole new structure into each of the slots. So here I have a graph inside each of the nodes of my graph. Fine. And here I have also a graph into each of the nodes of my graph. So those are two different ways to do duplicate. And this one is decomposing the graph structure little by little. And this one is actually rotating the graph structure. So meaning, by rotation, we mean that the focus of the graph that is inside this node being focused on is the A. It's A, right? Whereas here we're in B, but we have a whole graph in B. And what's that whole graph in B? It's the graph focused on B, and so on. So that's duplicate. And yeah, so how does it work? Well, that's a good question. Actually, I think I pretty much blindly copied the code. Well, I did add Spago and DAL, and added a few utility functions. But here's the code. Maybe I should actually just open the code somewhere in a window. It's actually going to be in libraries and in Purescript FGL, right? Yes. So inductive now has pointed graph. And a duplicate method, but duplicate is actually extend. And hold on one second. Yeah, there's Comonads can be described either by a extend or by a duplicate, and they have a relationship to each other. So you can define only one of those, and it will work. And in Purescript, the type class hierarchy is a little bit more detailed. So you actually have a comonad, that's the one that has extract, and extend, which is, as I said, similar to duplicate. So duplicate can be written in terms of extend, which it is here. Duplicate is extend identity. So extend takes a function f, and that's how it was written in Haskell. And this is my writing of it in Purescript. So I had to create a bunch of other functions, since also the FGL library is a little bit different. But basically we have something that's ultimately similar. Our key needs to be ordered. So yeah, let's look at the code. And also let's discuss what I'd like to do today. I'd like to do something that I discovered, which is that there is also a formulation for algebraic graphs in Purescript. And that's great because I really like this formulation, because one of the main reasons for that is that graphs are correct by construction. I think FGL graphs are also correct by construction, but the algebraic graphs, they have sort of a bit more structure to them. I might or might not use those in the end, but it's also interesting to discuss a bit how things work when you have an adjacency map under the hood to make the map work, which is exactly what FGL does as well. There's an impl module here with an implementation that's based on adjacency maps. The graph representation is a map of node keys to contexts, and then each context is has incoming edges that are an adjacency map, a label for the node, and outgoing edges, which is also an adjacency map. And in Purescript Alga, we have something similar, we have also a adjacency map here, and it's used, I believe, in I think basically there's a from adjacency map and a to adjacency map for the graph. Is that right? So anyway, let's also pull that, because the idea is well, let's spend some time understanding our own in the port that we did of the Comonad instance, and that how it rotates. And then when we understand that, let's implement also the Comonad instance for the Purescript alga. That would be a nice little self-contained thing. I hope I can at least get started on that. Okay, so what did we say we do? We want to clone this, and in this layout you can't clone it easily. How about that? Because I suppose it's rare to clone on tablets. Fine. So let's go down one zoom level. And see what we have here. Well, first of all, we have Spago, which is great, which means I can maybe even run. And which version of Spago does this use? 13.8, excellent. That's the one we have in our environment. And right, where was I looking at? I wanted to look at graph here. And I think, right, we have two adjacency map. And I think we have the reverse, don't we? From maybe that's just MK graph or something. It's not. So let's see. It's here from adjacency set. Maybe we have two graph. We don't. Okay, let's. Okay, the build succeeded with Hello Sailor. That's another. That's another one. No documentation here. So hold on. Graph A. Okay, so no, not here. So list of tuple to graph A, subgraph off, two adjacency map. So let's see if we can have maybe. Oh no, there's only one of those. Okay, so looks like we can convert a graph into an adjacency map, but not the reverse. So I don't think, and let's focus here. So I don't know whether actually the adjacency map is used at all as a as some underlying representation for alga here. It could be that that's not the case, and it could be that maybe I picked up some stuff also from the hackage docs. Adjacency int map, adjacency map, internal. Conventional graph data structures such as adjacency map, its various flavor, adjacency map specialized to graph with vertices, non-empty, blah blah blah. Large part of the API is available through the foldable like type as the algebra graph to graph. Interesting. So to graph takes anything that has a to graph instance and can run to graph on it, and then can do various transformations, and that's cool. Do we have that? I don't think we do, right? No, we don't. Okay, well, suppose we could have like a classy thing as well. So maybe that's sort of where things stopped in Thomas's endeavor. Okay. So we have some algorithms. There's an old instance and some other things. So there's not a lot of stuff there, but maybe we will need to find out where we are at and play with it a bit. And yeah, maybe write a test or two just and contribute that. Okay. So do I want to do that first, play with Alga a bit? Yeah, you know what I do. So let's remove the main, because that's going to bother us at some point. And yeah, let's have the docs open on this side of the world. Let's import algebra.graph. Sorry, import algebra.graph. And yeah, let's create a simple graph. Let's, for instance, G1 is going to be a graph of, let's say, unit. And that's going to be just the vertex unit. And then we'll maybe try and, well, let's see if it has a show instance. It does not. So let's see if we can maybe just do to something. Well, how about adjacency list? Yep, that's possible. And Spago test. And we have a tuple of unit and nothing else in it. Sounds right to me. So we have a simple graph. Let's create G2, maybe connecting two G1s. How about that? Because the point of algebraic graphs is that they have these two combinators, or well, algebraic operations on them, which is overlay, which takes two graphs and give you a new graph, and connect, which takes two graphs and give you a new graph. So this is going to be, I think, what's called a discrete graph. We are going to overlay the two, overlay G1 and G2. By the way, if you're a fan of this stream, you know that I've already talked about this particular graph representation when we were looking at the apart work. In this work, and that should be then in a blog post that should be linked somewhere, right? Well, I thought it would be, but it is not. Here, blog post would be here, and blog posts, and apart. Right, actually, the code I want to show is going to be here. Structures graph. So we looked at this because look, it has empty, connect, and overlay, and that's from Alga. And And I said previously on stream, and I still think that's the case, but I'm not sure, that I believe that this actually cannot write all types of graphs. That that will be stuck at some point because of the code-free construction. So even though it seems like maybe it's possible, I think ultimately there must be some mathematical thing there that doesn't work. I mean, my intuition is that, but it could be that I'm wrong. Certainly, it's not possible. Once you have a graph, it's probably not possible to get to another graph by arbitrarily adding a connect or an overlay, because a connect will connect that new node to all of the previous previous nodes. So at least it's not, cannot be incrementally constructed of in some ways. But yeah, that was the intuition. But anyway, that's one of the things, one of the reasons why we saw already this graph previously. And so if I overlay, I would need to overlay G1 and G1, and then you would tell me what the adjacency list would be, and that would just be that would just be again a list of tuple units. That doesn't seem right. It does not seem right. Maybe we'll want to have the Haskell library around. How about that? I think I have it somewhere, by the way. So we just need to probably just rebuild it. I think I must have moved it into dev, I think. Or stash, or cache. And build and workshop Haskell, and so it could be in graphs. Don't have graph here, and yeah, no, I don't see Arga here. I should probably find instead, but well, at least I import Alga somewhere in workshop patterns transforms. Is that right? No. No Alga here. Okay, no Alga there. So in that case, let's just import it into our usual folders in libraries, and I guess that's a bit of a of a detour, but I think it'll be worth it. To have a working implementation to compare. Okay, and well, do we think that that's just going to work? It's possible. Currently using stack 233, this version, okay. And then eval error attribute JC10.4 missing. But that's yeah, that might not. Is there is a cabal? Well, let's just cabal test. How about that? So okay, there's something going on. And let's go back to Purescript Aga here. And so I'm claiming that this is not right. That G2 overlay G1 G1 should probably be two of these things. But it depends if the graph parameter is supposed to be the unique key for the label for the node, then I suppose then well, let's try and create G3 connecting or creating an edge between G1 and G2. Okay. Well, oh, right. So it's not creating an edge. It is an edge. So yeah, probably adjacency list. Hold on, I need to display G3 here. So edge unit has, I think that's an edge. I mean, let's clarify what an adjacency list is supposed to be here. Adjacency list. Right, so it first takes it to an adjacency map and then an adjacency list. So maybe we should try and, I mean, is there a show instance for an adjacency map? I suppose that is one question. And not that I can see. Not that I can see. Adjacency set. A sorted adjacency list over graph. Sorted list of edges. Okay, I suppose maybe doing things with unit is a little bit hard, so let's do it with int and say that we have a vertex 0 and a vertex 1. And that, well, that GC is going to be two things, actually. It's going to be overlay GA, because we're still interested in what that's going to be. Come on. And GD is going to be overlay GA, and we're definitely interested in that as well. Okay. A little separator. And we want GB RGC and GD. And maybe we'll want to have some, okay, so maybe it is because technically it's the same node. So this is a unique identifier for the node. So, okay, so we're all good. Purescript simple spec, is that, or Purescript spec? Do we have spec in there? We do not. So let's import it. Spago install spec. And okay. Agency list and G1 should equal a list of tuple unit empty list. And we import a test spec after Spago build. And Haskell is still running and built, and it's actually running the test suite. And there's inspection testing. Look at that. That's pretty advanced. That I think is Joachim Breitner's work, which allows to look at core to know whether some properties of the data structures are respected. But looks like actually this works. So, well, that's pretty cool. But I don't know that we're going to use it right now. Another value should equal. Okay. Should equal is in assertions. And tuple will be in data tuple. And lists won't match array. Yes, so what should we do for this? We should do maybe two lists. Hold on, let's do list is yeah, that's from data list, right? Oh no, it's its own thing. It's oh hello. It's a special list. I think it's a way to do a lazy list with function trunks or something. Is it? An abstract list that is typed with O1 time concatenation uses different lists. A is a type of list elements. List A is a monoid, and empty corresponds to the empty list. And two lists can be contained. There's a mapend. Second list can be constructed. Okay. Instance of his list. Okay, this is all the surface features of lists. Oh, extract plain Haskell list. So this must have been lifted from maybe even Alga itself. Let's see. Internal. Yeah. Yes, indeed. Interesting. Monoid of endomorphisms under composition. Right. Yeah, so endo hello plus plus is going to put Haskell after. So if we just had endo hello Haskell, that's how it would be, but we have endo hello plus plus mappended to endo plus plus bang, and so that actually still takes only one string and puts it in between. So yeah, that's smart, and I think that that's just a way to yeah, I think build up a list instead of with a concrete constructor. It's like building it out of thunks, something like that. Okay, and where do we care? Because then we need to import that guy, and then we need to be able to construct one if we want to be able to compare one. And so, well, the EQ instance, so that's cool. We could do two array. Yeah, but maybe do two array is actually the simpler way. So let's do a two array of a Jetsys list here. I actually maybe we need to do this, and two array will be from algebra graph internal. So in theory, yeah, it's because of the internal list, right? So we could do from array. Yeah, we could do from array. Yeah, which is list and do append. Okay. That's not very nice to do it in this way, so we'll do just from array of this in this direction. And we'll test, except now we're not in the right monad. Is that what's going on? Yeah. Well, just put it there. How about that? That does not work either. Yeah, I think there's a run thingy. Isn't there a run thingy? Launch of prime run. Well, there it is. And we'll do that and do that. That's actually probably going to be okay as long as we have f and run spec. And console reporter. Apparently not being picked up, and then we're just missing the type declarations. That's all good, and we can test. And we do tests, and apparently reporter squashes all the things. No, yeah, it squashes them if it comes afterwards. So Okay, cool. So it doesn't add a 1 plus 1. It's okay. It makes a singleton graph. Overlays the same singleton graph, something like that. Don't really love these names, but we should probably not even. We should probably do something like actually use the constructors. I think there's a vertex constructor. There's a vertex constructor, an edge constructor, an overlay constructor connect. We could do edges too, that takes a list, but that's one of these crazy lists. So we can say something like, so that's going to be just a singleton graph, so we just say vertex unit. Don't need to give it a type, I don't believe. We just need to import vertex, so let's import all things, and then this will be overlay of vertex unit. Okay, and vertex unit. Okay, and it's not the easiest to read with the adjacency list. But, oh well. And then what are we doing next? We're doing we're doing an edge. It makes an edge. And so here we did edge unit, and that was going to be this, I believe. Spaghetti test. Yep. And then we can make, I mean, this graph is it's the graph over the terminal category or something, over like the one element category or something. So it's always going to be either the simple node or the edge, the node. Yeah, because it can be a node. We're not in a category, so in a graph we can have the node with no edge, and so there's only two possibilities. The node is just the node, or the node with an edge, and that's it. I think any combination. So if we connect, basically now, that's like we've done the extent of what we can do in this domain. And I think this is going to be this. indeed. And so that's connect. And then I think all combinations of this. So let's say if I now overlay like G3, for instance, yeah, it's still exactly the same graph. There's only two possibilities in that in this space. Okay, cool. So maybe it's more than the singleton graph, right? It makes maybe alga has a name for it. Deep embedding, define a num instance. Num instance. Okay. Do we have a num instance actually here? Num instance is just to be able to use plus to add the graph and multiply to connect them, which is cool. I wonder whether we can do that here. Num. It doesn't seem like we can. That'd be kind of cool to add, no? I think that'd be kind of cool. We have plus, and it means that we could just use plus and minus. That's what the. I mean, that's taking us just a little bit away from our goal, and but I suppose it's making us a little bit familiar with the library. So next time when we go at it, we know a little bit more what we're doing. What was I? Oh yeah, num instance. Numerics. So that will make us depend on numerics. Which I suppose is fine. Is that the main thing? Is that the main one? Are there other libraries that do numerals? This has the big int. It's pretty cool. It's a bit unmaintained, unfortunately. Type classes, number, Purescript numeric hierarchy. Okay. That's cool. HD Garo did it. Oh, right. So maybe the argument is to say, well, actually, there's no ring or semi-ring. I think, is it a ring? I think it must be a ring, right? Alga. If you ask plus and multiply, no. Ring does not satisfy the usual ring loss. No, it does not. Okay, that's cool. See graph for more detail. Because we don't have additive and multiplicative identities, and we don't have an additive inverse. Okay, so that's why. Okay, well, no, that's not why, but it's interesting. And let's see, complex numbers. It's in appendix. Cheat sheet. Oh, pretty. So yeah, I mean, I think this requires the absorbing and 0 and 1 sort of being their respective identities with the committee, with the distribution laws and whatnot. So, I mean, you can say it's a numeric hierarchy, but it's obviously more than that. And so the question is here, does this respect it? And well, yes, it does actually. Say that num is EQ, summary ring, and commutative ring. But so if we wanted to make a lawful instance of this, is there some part of the numeric hierarchy that we can hook up into that would work for us? And that's possible, but zero is vertex 0. I mean, this is all not exactly what I'm expecting, actually, right? Because A here, if it's the key type or the node type, then here we're saying a num instance. I'm not sure whether this makes a lot of sense here. I think, yeah, I think it's a bit confusing. It should be called A and whatever. But then from integer 0, well, it would depend on the graph, but would it be, no, it would be an empty graph, wouldn't it? Ah, here it's not. Here it's the, I don't know if this makes sense to me. Wouldn't 0 be empty and from integer be a single node? Okay, I think maybe not worth spending the time. That's a bit of a rabbit hole here. So let's not have numeric instances. What were we saying then? Well, we have a bunch of tests. We could add some for GC. It's already something, right? So what we'll want is to create instance Comonad graph, but no, because we want the pointed graph. So first we need to figure out what the pointed graph is, but there is a context thing here, which is slightly different than the context thing that we had before. So maybe we'll create a context prime, because I kind of want the A here. I kind of want the node, I think, in order to be able to have a focus. By the way, this is it feels a bit like maybe it's an implementation detail. Like it's super useful to have the outgoing and incoming and outgoing edges, but it sounds like you could derive it. So if we go back to our pointed graph, the definition of pointed graph is this. And so in our case, we don't have different things for they're not labeled. So that's another thing we could try, is to make labeled everything. But since this is not labeled, things are simpler. We should just say graph key, pointed graph key, and then context key, well, context prime key, right? But what I'm wondering is, can we just do like a focused graph that just basically has a node here? So if it's a node, then it's just a key, I think. And then can't we make a comonad of a focus graph and a pointed graph? And I think we probably can. Okay, thought we started, but we have not. Comonad focused graph, and we need to import comonad. Actually, we're going to do that automatically for us. Great. And where yeah, and then we need to import extend. So obviously extract is going to be super easy. Extract focused graph key equals focus equals key. Extend though takes an F and I believe a focused graph again. Of key and a graph. And yes, so that's where things become a bit more interesting, and we want the type of extend basically. And okay, I think I should remember the type of extend. Extend should have type what? I think it takes a to WB and a WA to a WB. Maybe it takes WA to B and WB. I think that's more like it. No, that doesn't make sense. It needs to take a WA, or maybe just an A actually. A to WB and WA. We need to extract to get the A, and then we get okay, I don't remember. WA to B and WA. Okay. So F will give us a B, and then right, and then we can't arbitrarily wrap it up in a W, because that's what a monad does. But what we can do is we have our WA and we duplicate it, and then we F map it. What? No. Trying to make the relationship with extend, and so if that's identity, yeah, right. So if that's identity, then it goes from a WA to a WA, and then we end up with a W of WAs, which is duplicate. Okay. So let's say it differently. If we have a comonad, a comonad of A's, so a space of A's, and that we know how to take a whole space and get a value from it, then we basically kind of duplicate that so that we have a WA full of, instead of A's, full of WAs, and then we apply the WA to B in each of these spots, and then we get a B, now a W full of B's. So for our graph, what does it mean is that we have a graph full of nodes. Let's not consider the edges for now. And then we create a graph which has all of these. We have a function that takes a graph and gets a single node or a value. And then we duplicate. So we can do that by creating a graph that has graphs inside each of its positions, and then applying our function f at each of these positions, which I think uses the functor instance, right? Like for that, we need to have a functor instance. It's a little bit, it's quite hidden by this implementation here, but I think map context is the kind of functorial version of it. I mean, here we also have labels, both labeled edges and labeled nodes. Okay, so let's see if we can do that. I mean, the truth is we could also implement duplicate and then derive extend from it. Duplicate is just WA to W of WA. And that might be easier to write for us. Because what does this mean? Okay, I did this again. It means that in the key, we put each value of the graph. So we need something to traverse the graph and change its value. So, well, don't we have a functor instance for the graph? We do. So then we just map. So where do we map? So it's a focus graph. That's one of the things, and it will be focused on a focus graph. That has a key. What that is the focus graph actually. So we can call that like this. So, and then its graph of graphs is going to be a focus graph. No, it's a graph of focused graphs. So Yeah, I think that's fine. And then we construct it. How? We say with map. Is that true? There's some function map that we can map over G, and that will. And what type we need to have? A non-class extend. Well, and please import those things from class Comonad. And right, and we would need to say that extend is what? It's not duplicate ID, it's probably like map f duplicate fg. Yeah, okay, yeah, true. Oh, extend focus graph. And yeah, so we actually kind of need this to be focus graph. And it needs to be specialized, which is fine. And we have a candidate for F, which is yeah, it's an A to a focus graph of A. Right. And that's the rotation. Right. Let's rotate or refocus. We could call it focus, I suppose. And focus is of type A to, or yeah, to focus graph of A. Right, and that's where we actually need to know that A is inside focus graph of A. But in this context, we do, because we map along G. So really, in this case, we can return focused graph A and G. G being a graph. Right. Yeah, so I think in this case we are taking A and we are getting focus graph of A of GG. No, focus AG, and then we pass that to G. I think that's right, but functor for focus map. maybe we can derive it. Derive instance functor focused graph functor focused graph. We can, and we did. Okay, so that's a Comonad instance, I suppose, right? Let's try and play with it for a second. Let's actually make this this guy. Which is not so easy to make, by the way, in alga mode. Well, we do something. How does it work? I'm tempted to do ABF. Yeah. Maybe I can do. Well, actually, since I can repeat node, I can do ABF and then FDCB. No, I can't do that. And then overlay them. Oh, maybe I can actually. Okay, let's try that. Let's do ABF. It's going to be a graph of char. And ABF is going to be, well, actually there must be a, there's path. That's cool. That's good. We want that. But we also want connect a given list of graphs. Isolated vertices, so maybe edges, the graph from an array of edges. That takes a list of tuples. Right, so we could do ABF. I mean, that's easy because that's the completely connected graph anyway. And if we connect, we could connect the vertices, but we need to construct a list. Still possible. Shall we try that? Let's try that. So we connect, and we need to construct a list. So we need to do from array, and we create some vertices. So we have vertex A, vertex B, and vertex F. And okay, apparently, yeah, we don't have G2 anymore. That's fine. And then we do a BCD. Oh, you know what? Let's do BCDE. BCDE. And we do that with the path. Right? There is a thing like that. One is to an adjacency map. Okay, hold on. And the other is to a graph. We want it to a graph, and we say B, C, D, E. And then I think we say G is a graph of char, and it's overlay ADF BCD. Okay, yeah, we don't need to put vertex here, which is a nice convenience. And then let's look show G just to see whether that has some sanity. So A is linked to BNF, B is linked to CNF, C is linked to D, D is linked to E, E is linked to nothing, and F is linked to nothing. That's a problem there. F should be linked to A at least, but connect doesn't do the cycle, so let's make it do the cycle. And now A, so let's, A now connects to A again, which we don't want. Okay, so it's not exactly that. Let's see. Is there a cycle? There isn't. Circuit. Excellent. Circuit, and then we can also do this, I believe. And we now have, oh, no, that's not right. A connects to B only. It doesn't connect to F. So not that then. Circuit is not that. Head, tail, head. Does sound like that's what we want. ABF. A to B, B to CNF. Let's log show ABF. A to B, B to F, F to A. Is this direct? This is directed. Is this meant to be directed? I think. Huh. How's this work in Argo? Directed. It doesn't even say. Directed. Bipartite, undirected. Undirected. yeah, it's a whole other thing, which makes complete sense, and I think we should have one of those. Not graph dot, yeah, undirected module graph algebra.graph.undirected, where pretty much all the things, but undirected. And I believe that we use the undirected adjacency map, maybe. Relation symmetric. Well, not directly actually. And then it has a transformation, which is cool. Okay. So what are you? You're UG of G graph A. Okay. Because we import graph as G, I suppose. Yeah. Import algebra.graph as G. And so UG should be G.graph A. But we're going to have to do all those things manually. Basically pattern matching on UG here. Yeah, we're going to need those guys from undirected and to undirected. Course is a thing that exists, right? Data functor contravariant. Normal graph to graph. I think that's like the new type thing, isn't it? I think basically it's just put UG in front, right? And to graph is from algebra to graph. Yeah, that's that classy thing we don't have here yet. But remind me what the type of it is. Oopsie. It takes any T to G graph to vert. Oh. Not obvious. Okay, let's drink a bit. And to relation, that's something that exists here. Oh, it's a very inefficient implementation. Okay. And r.relation, what's that? Oh, right. So that I have no idea. That sounds very interesting. And I suppose we should have one. A relation. And I suppose a symmetric. Take me to your leader. Indeed. Wow. Symmetric binary relations. There's also algebra graph relation. Okay. But I see. So some of the two relation logic hold on, how does this work? No, it's to relation itself is implemented in terms of r dot relation. Yeah. And it uses empty vertex overlay connect for 4G. Right. Okay, so I suppose if I only have those guys and the relation type, then I should be fine. So let's try. Algebra.graph.relation.symmetric. And we want the type relation 2. So show me what is that. Set new type. Sorry, I didn't get what I wanted. That I believe is what I want. But really in Purescript, these things are damn, but we import algebra graph relation, I see. Okay. Fine. We'll get to that as well. Module algebra graph relation. And the relation is this. Looks a lot like a category. And uses sets. Not sure we want to use sets. Imports data.set as set. We could try. With hoping maybe there is such a thing as a vanilla set here for us. If there is, you will also need a tuple. Data tuple. And yeah, well, set. And sure. Okay. And then the symmetric will import algebra graph relation as our, and it will be SR of our relation A. fine. And then there will be a from symmetric. That will be from right, from symmetric. We'll take a relation A and get a R relation A, I think. Yeah, by doing SR R equals R. And I suppose in that case we could have this dark here. And we could have empty, of course. So for us, it's just going to be empty equals SR empty. SR R dot empty. We're going to get to that. And then it's probably going to be pretty much the same elsewhere. Such that what we want is really here. And here empty is this, which makes sense. Yeah, I suppose we need to also do this. And oh yeah, we need 4 rows here. And that, where would you think that's a module? Okay, this is type constructor. Yes. There we go. There might be a better way to do this. Vertex. Okay, probably that would be a better way to do this. Vertex and set singleton X. With a for roll and overlay and connect. Ord from data ord. Union is from set union, right? So yeah, you also import union here. And domain. Domain is the, so it's x.domain. properties, and then we do domain, x.domain, y.domain. And that's where things are a little bit more interesting. There's a set product, and set product comes from where? Wonder. I wonder. It comes from algebra graph internal. And do we have it? We do. Awesome. However, we need to unpack that guy, which is fine. And forlay. And this compiles. Does this make this compile? With forlay, should. Yeah, except indeed it needs to have the right types. Let's go back here. Here. Indeed, all of that stuff. And all of that stuff, which is the same. And we need to import ord from data ord. And we need to say something. Right, this is just coerce, but yeah, we're going to need to say SRA, SR vertex A, aren't we? With parentheses. A is actually just A. Okay. Overlay. That's going to be SRA and SRB, and we're going to need to SRR overlay AB, I believe. Yeah. And that we're going to need for all. And then we need to do basically the same thing here. And this compiles. And we don't need that. And undirected. Well, we have two relation that works now, but we don't have two graph. There's many other things we don't have. But I'll stop here and I'll make a little note. Comonads. We started on, well, this basic tests for Purescript Arga. Actually, this is just Purescript Arga. basic tests. Check. Implement undirected graphs. Then Comonad for undirected focused graphs. And then maybe, you know, then maybe we'll do a Comonad for directed focused graphs. That's the same thing, right? Well, we do need to find out if context is needed. I get the sense it is, but and then maybe stretch goals, right? Labeled graphs. And by the way, just reminds me, I think there is a PR. At least, no, not a PR, a fork. Oh, I think, oh, I thought I submitted that thing. I'm pretty sure I did. Work in progress, right? Label graphs. I thought I did this weird thing where I submitted, or maybe I didn't press submit on that. Huh. I was pretty sure I actually had submitted a pull request on behalf of Anilanar there, which I thought was a weird thing to do, but I did do it. Well, I actually have at least a draft of it somewhere. Oh, there are even some specs. Oh, and an arbitrary instance for graphs. Wow, that's cool. So we need to look at that. There's graph and that branch with tests. Cool. So that's it for today. Thanks a lot for watching. I'm Junchan, and we'll see each other maybe on Thursday for more graphs and Comonad instances for them. Bye-bye.